Hello. I don't know what you mean by date, hon. Just make it today's date. Yeah, I guess. Gotcha. Okay. Yeah. Well, I'm in class right now, so I gotta hit the road. No problem. Hello, Christina. Quite a bit early. Do you have any questions or anything? Hey, John. You guys are early. I just checked in to make sure everything was working. I had some difficulties last night, but if you have any questions, y'all can certainly use this time to get those answered.
Give me a second.
You're a little too quiet. I can hear you, but not very well.
I have a quick question.
Okay, is this John?
Yeah.
Okay.
I haven't checked the what textbook we're supposed to use quite yet, but I was wondering if we're able to use like one of the older ones. Like
Yes, you have to have access to the online computer system that we're doing. If you have like a third or even, a fourth or even a third edition, I don't care as far as the physical textbook goes. In fact, if you really like a physical textbook, I would recommend you buy like the third edition or the fourth edition, because when you buy access to My Lab and Mastering, you automatically get access to an electronic copy of the new edition. And that's what we're working on, is we're working on the new fifth edition. And if I have to make like an assignment, like sometimes I might choose a problem from the practice sets at the end of the chapter. If you tried to do that with a fourth or a third edition, it would be a different problem in most cases. So by having electronic copy in your MyLab and mastering, you still have access to that in case something like that were to come up. So yeah, I don't care what you physically have as far as a textbook goes. A binder ready 4th edition, a binder ready 3rd edition, all that's fine. But you do have to have access to the homework website, which requires that 5th edition access code.
Okay.
Probably that's the cheapest route too. If you actually didn't want to book at all, the cheapest route would be just go into Canvas, click on MyLab and Mastering, which you'll see up in the left-hand side of the page, and then click on the yellow button that takes you to MyLab and Mastering. And there they'll ask you to probably make an account if you don't already have one, and they'll actually ask you for your activation code, which if you haven't bought it yet, you can buy it there, and that's usually the cheapest place. If you bought it at the student store, it'd be a little bit more expensive because, you know, they have to handle it, buy it up front. So they've got a little bit of overhead on that. So they up the price a little bit. But if you wanted the cheapest route with a physical textbook, that would be, again, buying that same thing, just the access to the MyLab and Mastering, and then buying an older edition of the textbook.
All right.
I've been working on this textbook since 2nd edition. It hasn't changed a huge amount of the actual, you know, text, but the problems have changed. They've changed some of the examples and made some corrections, caught some errors and stuff like that. But most of the changes have been in the problem sets, the order of the problem sets, the correction of the problem sets, and some brand new problems. Anybody else have any questions? Or do you have any more?
As of right now, no.
Okay. I'm having some technical difficulties with the syllabus. That should be either done tonight or first thing tomorrow. And I'll post it then. Any of you that had me in the past know it's pretty much the same one. But what I do, I'm going to also make a video of me explaining the syllabus, so I don't have to waste in class time explaining it. I'll just tell you that pretty much you have a lot of online tests that aren't worth very much, like usually like 20% of the course grade. And then you have 2 major proctored tests, which are proctored either at the testing center, or we might figure out some other ways to do it. And they're going to count like 45% of the course grade, usually like 15% for the midterm, and or excuse me, 25, like maybe 20% for the midterm and 25% for the final. Both of those are proctored. You're not allowed to use notes. You're not allowed to use, you are allowed to have an equation sheet, but you're not allowed to use notes or books or internet or anything like that. And then 20% is the lab course. About 20% is usually what I charge, what I give you for the homework, and about 5% for the conceptual homework. If you do extra credit, they're just going to add up as more dropped scores in the homework category. So right now, my syllabus will say that I'll drop your 1 lowest homework score. If I create an extra credit homework problem for you guys to do, though, then I'll increase that to 2. And that way, anybody that doesn't do it will get a 0, but that grade won't harm them. Equation sheets are not provided. I've been trying to get the textbook publisher to provide me one, and I've made several attempts at making one myself, only to find that about every, you know, semester, TCC will just erase it. So I'm sick of making it. I'm not going to make it again. So feel free to make your own. You can typeset it. You can just copy them. Basically, what I normally allow is there's a couple equations I derive myself, and I tell y'all should and can use these, and they're not even going to be found in the book. Those are allowed. The rest of them are just the equations in the book that are actually numbered. So if you look like in chapter 21, there might be an equation 21-3. It'll literally have a parenthesis, then a 21-3 after it, and then close parenthesis. All of the problems that are all the equations that are numbered like that in your textbook are fair game. So that's what the equations are. It is 5 after 5:20 now, so students are supposed to have been in here. I've got 11 of you in here. That's good. There's 14 enrolled. I open the floor again to questions one more time. Does anyone have any other questions? Okay. The other thing about my course, which again, I'm not going to spend a lot of time on the syllabus. I'm going to make a separate video explaining the syllabus. But I told you that basically your 45% of your total course grade is from your proctored midterm and proctored comprehensive final exam. Both of those are comprehensive. A small percentage is from your online test. A bigger percentage is for your homework, and then 5%, which is usually about usually the homework's worth 20%, and conceptual homework's worth 5%. The online test is worth, like I said, sometimes it's as low as 10%. But you get to do those. I usually give you 3 attempts. You're allowed to use open book, open notes. You can even do Google searches, but you're limited in time. The only thing you can't do is you can't get direct help from someone, either by them posting something on the internet after the test has been posted, or by communicating with you via text, email, or anything like that. So you're just not allowed to access anything created after I posted the test, just because someone could literally take the test, write down what they saw, then make a website real quick and post it up there, and then you go straight to that website and find exactly the problems. That's not allowed for obvious reasons, and it will bite you in the rear. The more help you're using on those on those actual tests, the worse your grade will be when you take the proctored test. So I've seen a lot of that. That's a widowmaker, and I don't really want it to be a widowmaker. I want those to be your opportunity to shine, because you're really learning the physics. So now, in addition to all that junk, there is 2 ways you can get extra credit. One way I've already explained, whereas if I give you an extra homework assignment or problem to solve or error to find or something like that, that's just going to count as another homework, but I'll up the number of dropped homework scores by 1. So that really only has the ability to cut out any bad grades you've made, because basically when you do an online extra credit problem, you either get 0 or 100. If you don't get 100, but you did it, then I'll usually get it back to you and say, hey, if you want credit for this, you need to make this correction. And then when you give it back to me, I'll give you 100. If you don't get it, you're just going to get a 0, or if you don't do it at all, you'll get a 0, but that's okay, because now, since I've made 1 extra credit, I'm dropping the 2 lowest grades instead of 1 lowest grade, so it doesn't harm you. And then the other way you can get extra credit is every test that I have, and I try to have a test every 2 chapters, I will have an online test. But for that online test, I'll make an online practice test that's usually really, really short. And you can take it a bunch of times, and every time you take it, it'll be different. What I do at the end of the semester is, and those tests, by the way, disappear once the test is actually taken. So there's no reason for you to take, there's no reason or ability for you to take practice test 1 after test 1 has been done. But you basically are going to, I'm going to take all your grades from each of those tests at the end of the semester and average them. If you ended up not doing one, then one of them's going to be averaged as a 0. But I'll take that total average of the highest grade you scored on each of those practice tests, and I'll divide that by 20 and just add that to your score at the end of the semester. So the reason being is, for some reason, students do not necessarily take me up on practice tests when an instructor takes the time to make them. That's a really bad long-term choice. So don't do that. So to encourage my students to do it, I give them this extra credit, and that's literally up to 5 points added to your final course grade. Any question on that? Yes, the extra credit questions on my lab count as well. I do them the same way. So there'll be chapters we're skipping, like we're not doing chapters 12 and 13, but we do go to chapter 14. So I make chapters 12 and 13 available, and you can just do them as an extra homework assignment. And, they might be able to replace, let's say, homework from chapter 25 where you got a 70 on. Now you're going to get 100 on it. So that's the way that counts. Anything else?
I have a quick question, Professor.
Go for it. Is this Young?
Yes.
Okay.
So the labs, so I'm scheduled for a lab. I guess when I signed up for the lecture, it required me to select a specific lab section, or like time and day. Is that something that can be changed? Like, could I take a different lab at a different day?
It's very hard to change. We set up that way intentionally so we can do very specific things, but on a case-by-case basis, we will evaluate it. So if sometimes you'll happen to have one student in the other class and one student in your class that both want to switch. If I can find something like that, we can usually do that. And sometimes it just happens to work out either way. But yeah, if you're wanting to, let me know and we'll see what we can do. I think I only have, for this class, I think I only have one other section, and that would be tomorrow morning at 9 a.m.
Okay.
If you are you going tonight?
Right. I think yes. Yeah, I am going tonight, but it just, moving forward, it would be difficult for me, just based on my work schedule. But I did notice there was a lab available on Wednesday mornings and Thursday mornings by you and Professor Roskovich, I believe.
Oh, she's doing a morning one. Yeah, I completely forgot about
Right.
that. That's 242 as well.
Right. Yeah.
Okay.
And
Yeah, you
so
can
I was
possibly
wondering
do
if.
that.
Mhm.
Ask her about it though. That just tell her, you talk to me. I'm the chair, so I've given you
Okay.
permission, and I'm giving her permission if it works for her. But if it doesn't work for her, she just won't have to do it. So, and I'll send her a
Okay.
text message to let her know. Okay,
Okay. I let her know as well. So yeah, hopefully we can work something out. Thank you.
sounds good. No problem. All right. Any other questions before we get cracking? Okay. Well, I'm going to actually, I am going to look for some demonstrations that I think would be helpful. I usually post them on your Canvas page. I don't know that I have yet, so I'm just going to pull it up here. And sometimes I have some problems when I'm showing the videos through here for obviously copyright reasons. That might be an issue, but I'm gonna post it, show it on here in real time, and sort of explain what's going on. But the opening section of chapter 20, by the way, let me introduce myself. I completely forgot because I was already talking about questions and stuff. I'm Billy Younger. I go by Mr. Younger. I teach physics and astronomy here at TCC. I've been teaching physics, astronomy, and mathematics since probably 1996-ish, roughly. At the college and university level, I've taught at East Carolina, Chapel Hill, NC State, College of the Albemarle, Central Carolina Community College, and TCC. And I used to teach at the TCC Chesapeake campus, which is what one of my classes is listed as this semester, but usually not. So I ABD PhD on my physics degree, meaning I've completed all the work for a PhD, except for the big thing, which is a dissertation. So it's not quite as awesome as it sounds. The really the big part is not the coursework, which I did do, and not the comprehensives and the writtens, which I did do, but in fact, the actual research. I spent about 12 years in college, so I probably would have needed to spend another year or two, but my advisor orphaned me. And I was also looking for a place to go because the job market was so bad. And I just happened to stumble upon a really good job and took that. So that's why I will be, hopefully not perpetually, but at some bar, it seems like I will be perpetually ABD, which means all but dissertation. My interests are mostly in general relativity. I've been playing around trying to read stuff in quantum field theory and quantum loop gravity and string theory and stuff like that. But I'm really interested in that, electricity, magnetism, a little bit of everything. But mostly I'm just a teacher. I like to try to learn, and I like to try to teach, and I like to try to use my ability to explain things to explain complicated issues to students. So I have a real sorted background and quite different than most students. I usually, a lot of students with degrees in physics usually have very good backgrounds where they did well in high school and middle school and grade school and all that good stuff. I was the opposite. I graduated third from last in a class of 60 after getting a mulligan. So I kind of sucked. But I got interested in it my senior year and took off and was able to win awards and scholarships and all sorts of cool quote unquote honors. But I'm still that same guy, so I'm trying to catch up and be more educated in the other fields from where I was lazy from third grade up through my senior year of high school. By the time I graduated high school, I only read 3 books total, and I've been trying to make up for that by reading various classics. But anyways, I also try to pepper my courses and lectures with some history. So I'll occasionally bring up the history of something, like with regards to what we're doing now. This course, we start off in chapter 21, which is on Coulomb's law. And basically what we're covering initially for up until chapter 31, I believe, is what we call electricity and magnetism. And that was essentially capstoned, if you will, in the subject matter by a guy by the name of James Clerk Maxwell, a Scottish guy who worked as a Lucasian professor of mathematics at Cambridge, which is the same position that Isaac Newton held. It's also the same position that Dirac held. It's also the same position that the creator of string theory held, Witten, and then Stephen Hawking held as well. Actually, Witten controls it now, but Hawking had it before him until he died. So it's a pretty prestigious position, and poor Maxwell died at a really young age from a horrible case of stomach cancer, just like his mother. And that was quite sad. And he died largely without as the due respect of his peers, partly because of some intricacies of the way the Cambridge University system worked back then. But he was brilliant. He was the first person to tell us definitively and work out definitively what the rings of Saturn were. In other words, he knew they couldn't be disks, they had to be individual particles. He had worked out the details of that. He worked out statistics regarding atoms and molecules at the microscopic level. He basically, luckily, these scientists, one of which was Michael Faraday, who was a very good experimentalist, but there were other ones like Heinrich Hertz and Volta and Galvani, various other people contributed to the experimental development. Coulomb, Cavendish, Gauss, various people committed to the study of electricity and magnetism for a long time, and it was a constant back and forth. And there were people that saw it as realists, like they were trying to picture mechanical things in nature to explain how magnetic and electric fields behaved. And then others were like, no, we don't have to do that. We want to think in terms of some grandiose field that we can't see, and all sorts of weird stuff was going on. And Faraday was sort of that last camp, but he was, believe it or not, really uneducated. He basically got through high school and was too poor to do anything else, but he decided he wanted to be something good and do something good. So he went to a library, believe it or not, and found a book, a self-help book. And it told him all these things that you do, like learn a language, master something, do this every day, write this much every day, little weird little things like that. He took it to heart. And then not only that, he found a book called Conversations on Chemistry, which was, oddly enough, this was a book written by a female in the late let's say 1830s, 1840s, something like that. And you can still find it. You can find it on, well, I found it on Project Gutenberg and downloaded it. It's really good. But basically, she was the wife of a medical doctor, and he was, both of them were very enlightened and interested in science and stuff like that. So they would follow various science demonstrations and demonstrators all over the Great Britain. And they happened to have a really good one in Great Britain who did a lot of chemistry demonstrations. And they would then, or she would then write about it as if she's talking to her fellow lady friends who were, doing laundry and the typical girl stuff of the time. And it's really great. I mean, and not only that, you can pretty much easily tell where science diverged from what they were thinking at the time versus where it is. So it doesn't really confuse you that way. Well, he found that too. So he went on and actually got a job with one of those main chemists that they were talking about, and ultimately took his job over and became a really brilliant experimental scientist. And even though he didn't have any mathematical background, he did such a precise and accurate job of describing his experiments. Maxwell was able to take that position when he got at Cambridge and read Faraday's notes and could just essentially write down equations to explain what Maxwell had, or what Faraday had done in sentence form and experimental form. Obviously, other people contributed, but Maxwell did. Maxwell took all the pieces from all the people, but a good fraction, if not the vast majority of it, was from Faraday and his experiments, and he was just able to write it down. Now, he wrote it down in the terminology that he thought was most popular at the time, using some weird potentials that a lot of people don't use anymore. For instance, a vector potential and a scalar potential. But he also had a friend by the name of Hamilton, not that Hamilton, but that guy created a system called quaternions and thought it was the greatest thing he ever did, and even has it on his tombstone. But there's just not very many people that know much about him. So he thought that was the next big thing too. So Maxwell put Maxwell's equations in terms of quaternions. So when he published it and then died, because it was such an abstruse language and stuff like that, not very many people locked onto it. But luckily, another fairly uneducated person that quit school at the ripe old grade of 6, if I remember correctly, had passed, had more or less come in first place on the senior test in school and was shown to be brilliant, but he's too poor, he couldn't go anywhere. So he was working in the field of electricity and magnetism by putting a cable across from Great Britain to America, specifically to Nova Scotia and stuff like that in Canada, and then down to America. And his, I think it was his brother-in-law. It's either his brother-in-law or his uncle-in-law was a guy by the name of Wheatstone. And Wheatstone got him a job working in that. And he quickly became really good. Like everybody could tell this man knew what he was doing. He could tell them where to dig up the wire that was running under the ocean and tell you within 100 meters basically where you needed to make the repair. And he was really good at it. However, being uneducated and not gone through the military ranks, he didn't get a lot of respect and he demanded more money. And by that time, he started reading Maxwell's stuff. And he was like, wow, Maxwell's stuff will really help us out here. And he starts explaining that and writing his own papers. And he asked for a pay raise and they wouldn't give it to him. So he said, okay, I'm more interested in discovering this stuff. So he quit his job and went and moved in with his parents and lived with them for the rest of his life with literally no income. But he, Oliver Heaviside was his last name. He went on to rewrite Maxwell's equations in a new type of mathematics that he and Stephen Gibbs from America independently co-invented, and that's called vector calculus. And that's largely what you're going to learn about this semester is vector calculus. But if it wouldn't have been for him and a couple of his friends, it probably would have took more decades more for someone to understand what Maxwell had done. So we owe a lot to him. So that's sort of the history of where this came from. So that's what we're doing in this course is we're first doing electricity and magnetism. When we're finished with that, we're going to jump back and hit thermodynamics and kinetic theory. And then when we're done with that, time allotted, we will go into quantum mechanics and maybe even as far as nuclear physics after that. So that's why you'll see in our course, we have pictures of Planck and Einstein and Bohr. They are the creators of basically quantum mechanics, but you also see a picture of Maxwell and James Clerk Maxwell, the brilliant physicist from Cambridge. So anyways, we're going to get started on that. I have these neat little videos and I highly recommend you look for them. They're physics demos done by MIT. That's the Massachusetts Institute of Technology. By the way, MIT has what they call open courseware. So you can look up any course they have and they actually have it usually filmed. Sometimes it's just the notes, but sometimes they actually have it videoed and you can just, take a MIT course here in, rural Virginia or North Carolina or wherever you might be, not charge anything, but you get, if you think your class isn't good enough because, this goofy guy, Mr. Younger's teaching you, you can get the world-renowned physicist from MIT to teach you for free. So it's kind of cool. But what I'm going to do now is I'm going to go ahead and share my screen and show you some of these demonstrations because it's really interesting, some of the demos that I would like to do, but just don't have the time to do it because at the end of the day, it's way more important that you guys learn how to solve physics problems and you can get the concepts as well as we go. So let's see what I can do with this. I don't know why that one is there at all. Okay, so this one right here is what I'm looking at. See, it says MIT physics demo. This is a Van de Graaff. We're going to talk about that. But let me click on this real quick, and they're probably going to make us look at a commercial because we always do. Okay, now I can skip the ads. And let me roll this back a little bit. So I'm going to talk about this a little bit. The sound's not that important, but they're doing a Van de Graaff. So this thing right here is a Van de Graaff. That silver spherical thing on the top is just an aluminum sphere. If you were to take it up in half by lifting up that top half, what you see is down inside of the bottom of it, there is like a Teflon spool or axle. And then there's a really wide, like 3-inch wide, 2.5-inch wide rubber band going over that spool and running down to another Teflon spool that's down here in the base. In the base, there's an electric motor that spins that plastic or spool and a Teflon spool, and that causes the rubber band to go around. And just like how your feet sort of scrape on the carpet and you then go to grab a doorknob and shock yourself, that sort of same static electricity thing happens when you separate a rubber band from a piece of Teflon. The rubber band seems to have a little bit more affinity for the electrons than the Teflon does. So you end up charging the rubber band with little negative electrons. And then because it's not a conductor, the electrons pretty much stay where they are. But when the electrons get up to the spool at the top, inside of that sphere is a little wire that's connected to the aluminum sphere. It's a copper wire. And then they've got sort of a stainless steel piece of screen mesh with the little ends of the wires of the screen sticking out. They act like lightning rods. And in fact, the little electrons will see those and see that they're connected to ground, or basically connected to something that has zero charge. And that compels that metal in the screen and in the cord, the wire, and then in the aluminum, that compels the negative charges in that metal to run away, so that the metal starts to look positive to the electrons, so the electrons jump to it. That slowly causes electrons to accumulate all over that sphere, and you end up getting a giant, I'm guessing that rubber is stealing electrons instead of the Teflon stealing electrons. So it could actually be exactly the opposite. There's ways to tell, but I just don't remember off the top of my head which one it is, but I'm pretty sure it's electrons are building up. But the electrons are building up on the aluminum sphere, and because they are like charges, they repel. So the electrons want to get as far away from each other as possible. That means they all orient themselves on the outside edge of this sphere. And since the sphere is a conductor, they're free to move, so they do that. And that, in fact, creates basically a large amount of charge. You can build up, 30,000 volts on this quite easily. Down here at the bottom, there is a ground wire going into this ground plug. So this would actually connect to the little semicircular mouth-looking thing in a light receptacle. So that particular probe would be connected to that particular part of the cord that plugs into that particular part of the light socket. And then the other parts, of course, drive the Teflon spool that rotates the rubber band through the other spool once you turn it on. This wire is then connected, of course, to this rod that has another piece of metal on the end of it, and that's a direct connection to ground. Because if you actually walk by one of these, and that's what I normally do in my demonstrations, that I'll walk by them and I'll put my knuckle really close to it, and lightning will strike and shoot through my knuckle and cool stuff like that. And if the room's dark enough, you'll even see the lightning hit my hand, and you'll see it shoot out the side of my shoe and jump over the rubber of my shoe and into the floor. It's not painless. It's just, unless I did something really stupid, it's not dangerous. It hurts a little bit, and little negative charges are jumping through me. So that's kind of stuff I do. But anyways, if you don't want that to happen at random, you can keep this little grounding rod between you and the sphere, and then any of that lightning that tries to reach out and get you will go to that sphere instead. Over here, they're going to have a metal pole with a metal rod and two metal balls connected to the ends of the rod. So let's go on with this and see what happens. So this is like fishing string right here and here. So that's essentially an insulator. So if any charge were to get on this metal ball or this metal covered ball, it's not going to go up those strings. And it's also not going to go across here, because this is like a plexiglass tube, if you will, or a plexiglass cylinder, if you will. So nothing's going against that. Not only that, the fishing strings hung from like another Teflon cylinder, so that basically charge is not going to flow. If you get charge on this ball or that ball, it's going to stay right there. Let's continue. So now what's happening is he was keeping himself from getting shocked, also keeping lightning from striking the little metal balls on the end of the plexiglass. But remember, the metal balls that are on the end of the metal rod, they're actually connected. So what's going to happen is, as that, we're assuming the Van de Graaff turns negative, as that Van de Graaff gets a negative charge and like charges repel, that means the electrons in the conducting spheres, which is both sets of conducting spheres for that matter, since they're in a conductor, the electrons are actually free to move about the entire metal. They're sort of like a child with feckless parents on an aircraft, and the kids running back and forth on an airplane. That's what electrons do in conductors. So what's happening is, while that Van de Graaff is on, it's getting more and more negative, and that's forcing more and more negative charges to leave the gold sphere on the right of the metal rod and enter the gold sphere on the left of the metal rod. So the metal rod is actually becoming negatively charged on the left side and positively charged on the right side, but the net total charge is 0 because it's more or less isolated from ground by that wooden table and probably some stoppers on the bottom of that little three-legged stand. So that's what's happening if this plexiglass wasn't there with the balls, is you're just getting the ball closest to the Van de Graaff turning more positive, and the ball farthest from the Van de Graaff turning more negative. Now, when you bring the other two balls connected by insulators up there, then what's going to happen is when the whitish right-hand side ball touches the right-hand side gold ball, it's going to basically steal half the charge of the gold ball. So if the charge was positive 100 coulombs, which it wouldn't be, that's a big number. If it was, then all of a sudden, both of them would have a charge probably of like 50 coulombs positive. The same thing happens on the backside, of course, but that makes it a negative 50 and a negative 50. So when you pull this contraption away with the plexiglass, the white sphere, which is closer to the Van de Graaff, is now going to have a positive charge, and the goldish sphere on the other end of the plexiglass tube is going to have a negative charge. And in fact, like charges repel, unlike charges attract. So it's constantly, the white sphere is going to be constantly attracted towards the Van de Graaff, and the back sphere is going to be repulsed and should ideally orient itself so that it's farthest away as possible, assuming there's not a lot of tension in the string that's holding it, and there's not wind and stuff like that. So let's watch. See, not only is it keeping the white side near, it's actually keeping the line radial if you go slowly enough. So it literally forms a line pointing towards the center of the sphere. And that's what Coulomb's law tells us, is that the force of attraction or repulsion is directly proportional to the product of the two charges, and it acts along the line connecting the centers of the two charges together. It's also inversely proportional to the square of the distance between them, and we'll discuss that. So this is a Mylar balloon that's basically like aluminum foil. So it's aluminized, it has a conductive ability, but it's got helium in it, and then the balloon's attached again by like fishing strings. So that's a really good insulator, keeping it away from the ground. Again, we're going to leave it there, but we're going to excite a Van de Graaff accelerator by making the sphere become negatively charged. So what do you guys think is going to happen to this balloon as this Van de Graaff becomes negatively charged?
Is it gonna like float towards it?
Yes, but can you think why? Can you go deeper and understand why? What's going to happen to the metal's balloon that makes it want to go towards the Van de Graaff? Anyone? It's not easy. I'm not, this is not something I've taught you yet. So it's not something you're supposed to know. So don't feel bad about not knowing it. I've just given what I told you before. There's a little bit of enough, there's pretty much enough information for you to figure it out. So the helium-filled balloon is made of a metal. That means it's a conductor. That means charges are free to move around it. So if the Van de Graaff becomes negatively charged, what's going to happen to the part of the balloon closest to the Van de Graaff? And you can speak out. I don't see the chats right now. Anyone? So remember, atoms are made of, they're basically a nucleus that's positively charged with some neutrons in it too, but then there's these loosely tethered negative particles called electron sort of orbiting around it, but you know enough to know that that's not exactly right. And because it's in a metal, it turns out that the individual atoms are more attracted to each other than they are to, you know, one of their outermost electrons, maybe. So those outermost electrons are free to move around the entire metal, not hang out only by its atom. So these electrons which they're negatively charged, just like the electrons in the Van de Graaff. They're like charges with the Van de Graaff, so they are repelled by the Van de Graaff, and that will compel them to run around to the far side of the helium-filled balloon, so that the helium-filled balloon will become positively charged on the left half, the half closest to the Van de Graaff, and then the balloon will become negatively charged on the right half. That's inducing a dipole moment, if you will. It's inducing an electric dipole, which is where the net charge is zero. A dipole has a net charge of zero, but half of it's negative and the other half is positive by the exact same amount. So that's what happens, just like we did with that rod, the plexiglass rod and the two spheres, only now it's a continuous body. So the left-hand rod, so their left-hand rod, it's telling me hit okay, but there it is. So the left-hand rod side of the balloon is becoming sort of like a positive charge, like the white ball was, and the right-hand side of the balloon is becoming negatively charged, like the grayish ball on the other end of the plexiglass tube. So, now he's going to play a role in this too, the actual demonstrator, you'll see. Okay, so it might not be that easy for you to understand why this thing rushed towards the actual demonstrator, but I think you can figure out why it rushed away from the Van de Graaff after it touched the Van de Graaff. Anybody have an idea what happened there? Why did the balloon run away from the Van de Graaff after it touched it?
Did some of the electrons from the thing pass to the balloon?
Exactly. So the metal of the Van de Graaff and the metal of the balloon is all one big conductor. And a conductor is what we call an equal potential. Ultimately, we'll learn that that means it has the same voltage. So in order for it to have the same voltage, basically a buttload of charge is going to leave the actual Van de Graaff and go on to the balloon. That's why I was giving you the argument earlier that if the charge was 100, it would split between the two of them at 50 and 50. Something like that's going on. So now all of a sudden the Van de Graaff, which might have had, let's say 100 coulombs of negative charge on it, now it's going to have negative 50 coulombs of negative charge and the, or excuse me, negative 50 coulombs of charge. And then the balloon's going to have negative 50 coulombs of charge. So they're actually like charges, they're going to repel. And that's what gives a large force to the helium-filled balloon to make it run away. But the other part is when it gets back to the top, it's far enough away. But remember, now it has a net negative charge, and a net negative charge is always compelled to go to anywhere where there's a free access to ground. Same thing with a positive charge. They're trying to run from ground, go into a negative, something like that. So it can sort of do the same thing that the Van de Graaff did to the balloon. The balloon can do the same thing to the demonstrator. The problem is the demonstrator is not made of metal, so it's not quite as good. But if you've ever done the trick where you could take a rubber balloon and rub it on your head, well, not my head's mostly skin and sweats. so it don't do it very well anymore. But if you have a little bit of hair left in your life, I bless you, and I'm angry with you for having it. But still, if you do have hair left on your head, you can take and rub the balloon on your head. And then you can take the balloon and stick it near a wall or even a ceiling. And what will happen is that balloon, being made of rubber, has a collection of charges, probably negative. I think the rubber band has more, or the rubber has more affinity for the electrons than your hair does. So it'll have a wad of negative charges on that one part of the balloon where it was touching your skull or your head. And then when you brought it near a wall or a ceiling, the wall and ceiling are not conductors, but they've got atoms in them and molecules in them. And those molecules hold on to their electrons, but the electrons are constantly moving. So you can actually compel those atoms or molecules in that non-conductor to sort of say, hey, man, there's a negative charge coming near my surface, man. You got to keep that away from me, dude. So the little negative electrons will run on the other side of the actual non-conducting atom or molecule, making the side of the atom or molecule facing the balloon, making that actually look positive now. So then all of a sudden, this boy, in the same sense as the wall, will look positive to that negative balloon. So the negative balloon will charge towards him and hit him. At that point, the charge from the balloon, knowing that the boy is ground, basically, will flow into ground but through the boy, and now the ball is again neutral, or the balloon is again neutral, so it'll try to stand back up and the whole process will start over again. Does that make sense? Anybody have any questions on that? So that part where they actually touch, that is actually charging something, not inducing a polar charge, but actually charging something by what we call conduction, because it literally touched. Normally, these other things are just called inducing a charge, and you can induce a net charge of 0, but you can induce a dipole moment by making one side positive and the other side an equal amount of negative. So that's some of the terminology we'll be using, and I just wanted to get that through to you. So now you might be thinking, hey, I bet you can do something neat with this and like make some kind of cool machine. And yes, you can. So here we go. Notice it's connected by a connecting rod, a conducting rod, and a wire. And a chain that's conducting. And this guy in the middle is isolated from it, as are the two little sinkers there and there. So let's see how that works. Let's imagine it hadn't started yet. So this thing over here, the Van de Graaff, is getting negative, 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 negative. Well, that's compelling this bell to turn positive, 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 positive by forcing the electrons down this chain across this metal rod, not down those strings because they're not conductors, and not down this pole because that's not a conductor, but all the way to this side. So this bell over here is becoming negative, 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 while this bell is becoming positive, 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 positive. Well, we can assume this hanging ball right here was initially grounded, say. Things that have charge, generally, the water in the air will get near them enough, and water being a polar molecule has one side that looks positive, the other side that looks negative, and that pretty much pulls the charges off of anything that's just sitting around. So if you charge something up and you come back hours later, it's often no longer holding charge. Capacitors are a different thing, though. If someone charges up a capacitor and you go and wipe and grab the two terminals, you're going to get hurt, possibly even killed if it's bad enough. So other than capacitors, most things and things with capacitance, most things don't just hold on for charge forever. So this thing's going to sit here grounded. This little ball is sitting here grounded. And as this bell becomes more positive, then this ball, the right-hand side of which is going to come more negative because the positive are running away from it. And that positive on the left-hand side is going to compel the right-hand side of this middle bell to become negative. So it'll attract that way too. But ultimately what happens is, because the right-hand side of this little ball, hold on a quick second for that, because the right-hand side of this ball is getting a net negative charge, that means it's attracted to the bell to the right. And it will, when he first takes this thing off of it, it will hit the bell on the right first and then go back, and the whole process will start over again, just like the balloon going back and forth between the Van de Graaff and the demonstrator. So let's watch it. Pretty cool, huh? So you can check that out. You can see that guy when he's doing his videos. If you just go to YouTube and do a search for his videos, you'll be able to find it. And now I can't find out where this is. I'm looking for others.
When the stakes are high at work, your tone matters. Grammarly's advanced tone suggestions can help. Because when you write with just the right confident tone, you can meet any challenge.
Sorry,
that moves
folks,
your
I'm
project
trying to
forward.
find my browser. And where it went.
Grammarly's advanced tone suggestions can help you find just the right personable tone to motivate and build trust with your
Oh, it
team.
minimized. That's weird. I have no idea what's going on. That was long. My screen has layers, so that made it. It's literally put it off to the other side. I didn't know where it was, so I was lost. All right. Anybody have any questions on that? Sort of that's the intro to things like conduction and charging and polarization that the book does in the early parts of chapter 21. Now I want to go into well, I want you guys to look more for more of those videos from MIT. I also want you to look at my YouTube channel, which I'll say now so that you can see it. Anybody willing to type it into the chat so someone else can copy it, that'd be great too. But the YouTube channel where I post my videos from physics, astronomy, and sometimes math as well, trigonometry, stuff like that. It's www.youtube.com/Billy, B-I-L-L-Y with the B capitalized, Younger, Y-O-U-N-G-E-R with the Y capitalized, physics, P-H-Y-S-I-C-S with the P capitalized, solutions with the first S capitalized, S-O-L-U-T-I-O-N-S. And that's it. That's my YouTube channel. Basically, when I teach an online class, usually within the same night of teaching the class, I will make the video into an appropriate format and upload it to that YouTube channel. If not, it happens first thing the next morning. So you always have that. But that also means you have access to past classes where I've done it. If you look in the videos on my YouTube channel, you'll see that you have that little description section in the bottom. And if it was done for a class, you'll see something like PHY242 underscore, or maybe just a space, and it'll say like 082522. Now, what that means is PHY242 means it's this course, and then 082522 means, oh, it was obviously in August 25th of 2022. That's helpful because one, that tells you when it was done. So if you just watched another video that happened to have been, say, the 23rd, 082322, then you know, oh, okay, so this must have been the class right after. Not only that, it also, because some of those videos were made before I had an iPad, so I was using a document cam with a piece of paper, and I had bad internet reception, so some of the images don't come out that good in my writing. But what I've done is I've made photographs of all the notes I took, so you can download them from my Google Docs. And in Google Docs, you will find that particular notes by doing a search for 082522. So when you find that, you just need to make sure that you're looking at 242, and that will be the notes. So you can just download it as a PDF. Okay. Any questions on that? I do the same thing with the notes that I take during class, as I put them on my Google Docs. And the link to the Google Docs will be in, and I think it already is, but it will be in your Canvas course. So any questions on any of that? I now have access to the chat again. I see that Ethan has written something. He asked about the relative speeds. A lot of that depends on what the initial conditions were. Like when he started it up a second time, those things weren't sitting perfectly still. So if it had just a little bit of velocity to the right, that would make it hit the right one faster. Or if it's just a little bit closer to the one on the right, that would make it hit a little bit faster. All sorts of stuff like that. In general, there shouldn't have been much asymmetry. The only asymmetry that does come from it is obviously the bell closest to the Van de Graaff is going to have the most positive charge. The next one away will have slightly less positive charge, and the next one away will have less positive charge still. In fact, that one would be negatively charged because that's where all the negatives ran from the first bell. So yeah, some of that stuff plays into it, but it's a very small difference between one bell and the next. However, as I told you, Coulomb's law, which might have been called Cavendish's law and might have been called Franklin's law, because it turns out all three of them did the experiments. And in fact, Coulomb wasn't necessarily the first one to do the experiment, but he definitely was the one that published it first. We have evidence that Cavendish did it sometime before him, and Ben Franklin did it sometime between Cavendish and Coulomb. So that's kind of interesting that we've got our American guy still in the game. In fact, Ben Franklin's the reason that we now use positive and negative. It was his idea to say that this one type of charge, when you rub, say, rabbit fur on a piece of rubber, the rubber gets a certain type of charge, which he would call negative, and the rabbit fur gets another type of charge, and he called that positive. And there's ways you can create that. And you can go by ranking. You can now take that rubber and rub it against something else and see if the rubber still gets a negative charge. And you can do that for a bunch of different elements. And then you do it for, rabbit fur against a bunch of different things. And slowly you can build up a chart where it has these things at the very bottom are almost always going to get the electron. And this thing at the very top is almost always going to lose the electron. And by putting them in that order, you can then say, oh, well, I'm taking this one and this one. So clearly this one's going to gain the electrons and this one's going to lose the electrons. Bit by bit, that'll allow you to figure out what materials do what. And it's called electron affinity, or electronegativity is another phrase that they use in that. That's more in the chemist world, but that gives you some idea what's going to happen. There's ways you can do it also with just a little device that you can use to measure charge. What I do is you can take a piece of copper wire with no housing, for instance, maybe a number, let's say a number 10 wire, or maybe even a number 12 wire, and just make it into a little knot, come down, do a swirl, and then go down and do a hook, and then hang from that hook 2 little blades of aluminum foil. Just by poking a hole through the little rectangular blades of aluminum foil, they'll just hang there like this at the bottom of the hook. And then you, of course, have that hook suck through, say, a Planters peanut bottle, and then the metal wire comes down, and that little loop keeps it from going into the lid of the peanut jar, and then goes into the peanut jar. You thread it down, then you've got more or less not a vacuum, but you have an area where wind's not going to blow the metal. Now, if you take that, let's say the rubber, and rub it against the fur of a rabbit, and then hold the rubber very close to the top of that copper wire, what's going to happen is that charge is going to compel the charges in the top of the copper wire to run away, because the rubber's negative, and the negative charges in the top of the wire is going to run down to the bottom, and it's going to distribute itself on the individual blades of aluminum foil. So the aluminum foil is going to spread out like that. And if it's a lot of charge, it'll spread like that. If it's a little bit of charge, it'll spread like that. Now, if you did the same thing, again, not necessarily touching it, let's say just holding it up there, and you pulled it away, the things would fall back down because the net charge was 0. But if you took the time to actually touch the wire, then by conduction, that little hook of copper wire and that little those little aluminum flaps would become negatively charged. Now, if you come by and take the rubber and rub it against the bunny rabbit's fur, you rub that like that. Now you take the fur and bring it near the top of that aluminum wire. Now that one's going to be positively charged, and that's going to compel the negative charges in the flaps down at the bottom to run up that way, and the flaps will suck together. That's how you know they're oppositely charged. So that's some of the ways you can do stuff like that. And it's very interesting, but it's also fundamental physics stuff that you'll see when you start doing your concept questions and so on and so forth. So remember your homeworks. Every week you'll have usually 2 homework assignments. Is one for homework where you're actually solving problems, and another one where you're doing conceptual problems. And they're essentially due. Usually we go at a rate of about 1 chapter per week. So this week on Sunday, actually, I think I'm going to move it to Monday since you guys meet on Tuesday. But on at 11:59 p.m., your homework will be due. And every Sunday, or excuse me, on every Monday, it'll be due like that. Okay. So this week we're doing chapter 21. I've now given you some intro to Coulomb's law, as well as some intro to how physics behaves. So let me do some quick calculations and show you some stuff. Anybody have any questions before we get started? We only got like 11 minutes. Okay, I'm going to turn on my iPad. And you guys will need a calculator, so hopefully I can get you guys to do that, because it will take a lot of time if I have to do the calculations myself. So I'm going to go ahead and share my iPad screen, and I will tell you what Coulomb said regarding his Coulomb's law, and that will hopefully help us get some understanding. And it's not unlike Maxwell. I mean, it's not unlike Newton's law of gravity. Those of you who had 242, you remember or 241, remember we covered Newton's law of gravity. And Newton's law of gravity said that basically the force of gravity is directly proportional to the product of the masses, and the force of gravity was inversely proportional to the square of the distance between them, right? Well, Coulomb, which by the way is the last name of the scientist who's given credit for it, and it also happens to be the name of the unit we use for charge, and that's a very, very big unit of charge. It's a Coulomb is a whole lot of charge. In fact, if 1 Coulomb were to hit you in a single second, that would easily kill you. It takes about a milliamp, and a Coulomb per second is essentially a whole amp. So it's 1,000 times what's necessary to kill you. So if you want to do F Coulomb, what Coulomb said was not unlike what Newton said. He said that the force in this case, instead of always being attractive like gravity, in this case, the force is repulsive for like charges and attractive for unlike charges, you know, opposites attract, that sort of thing. But it's still proportional to the product of the charges. And instead of using M, we use the symbol Q for the charge. And lo and behold, he found that the Coulomb force is also inversely proportional to the square of the distance between them. Again, that means if you double the distance between them, that is increasing the distance. That means the force will decrease, but not by 2, but by 2 squared, which is 4. In that sense, it acts just like gravity as well. Now, the other thing, and this is also something that Newton had to say with gravity, is he's actually talking about point charges, infinitesimally small charges that have no physical dimension. Essentially, what we think an electron is. Electron seems to have no physical dimension. And what he would say is that the force of attraction or repulsion is parallel to the line connecting the 2 charges. So if you're thinking 2 charges are point particles, then there's 2 points in space, and that's all that's needed to define a line. Therefore, the line going through it will be parallel / anti-parallel to the direction of the force. So that's something we've got to understand to be able to solve these problems, because we have a formula that can calculate a magnitude, but then we have to make it into a vector. Okay. Now, ultimately, there's a couple ways of doing it, and one I hate and one we're going to use initially is the one I hate. But the Coulomb force basically is equal to K Q1 Q2 over R squared, where K is approximately equal to 8.99 times 10 to the 9th. And that turns out to have units of newtons meters squared per Coulomb squared. Another way we might write that, and this is the way I really like, which is, you'll see it's kind of odd for me to say it, but you'll see why ultimately in this course. Q1 times Q2 over 4 pi epsilon naught R squared is the other way. And that's the way most people use it nowadays. They don't use this K, they use this epsilon 0, which is called the permittivity of free space. I like to think of it as something related to how easy it is for air to be polarized or made into a conductor, something along those lines, but it's really a fairly nebulous definition that I haven't worked out completely. So in this case, it's 8.85 times 10 to the negative 11th, or excuse me, 10 to the negative 12th. And this is Coulomb squared per Newton meters squared. Okay. So that's the difference between them. But what I want you to think, yeah, go ahead, Michael.
What's after the 4?
It's a pi, the letter pi.
Oh, it's pi. Okay.
Mm-hmm. Just to give you some perspective, G from gravity. Remember, we should, since G and K are in the same spots in the equation, namely in the numerator, those should be compared to each other, not G and epsilon 0. But G is 6.67 times 10 to the negative 11th kilograms squared per Newton, or excuse me, I made a boo-boo there. Let's find my eraser. You go away. That's Newton meters squared per kilogram squared. So this number is a 0 this G, this capital G, is a 0 followed by a decimal, followed by 10 zeros, and then a 667, whereas essentially K is 9 billion. So you can already tell that when we study electricity and magnetism, the force of gravity is going to be nothing compared to the force of electric propulsion or attraction. Okay. However, both of them by these equations reach out infinitely far across space because there's no value of R you can put in there that makes the F go to 0. Okay. So let's start off with a little simple problem. Let's say this is my y-axis. This is my x-axis. This is at 5.00 meters. This is at 3.00 meters. And this is 0.333 millicoulombs. And this one's negative 0.333 microcoulombs. And I'm going to call this one Q1. And I'll call this one Q2. So I would like to know what is the force on 1 due to 2. Notice that description I just said, and notice the symbol I used for it. The force on 1 due to 2. Okay. So what we're going to do is just use Newton's law, or excuse me, Coulomb's law, and work it out. So obviously, we first got to decide which is the direction. Now, remember, force is a vector quantity, and this is the way you're going to do it. You're probably never or very seldom will you actually put the sign of the charge into that formula for Coulomb's law. In other words, this formula and this formula, it is very rare that you put in a, oh, excuse me, not that second one. This formula or this formula, it's very rare that you actually put in a negative sign for the charge. Okay. What we do is we use our understanding of physics, and our understanding of physics tells us that like charges repel and unlike charges attract, and that the force of attraction or repulsion acts along the center, acts along the line connecting the centers of charge of the individual particles, which hopefully are infinitesimal. But if they're not infinitesimal, we can just sort of define something as the center of charge and go from that for one charge, and then do the same thing for the other charge. And then the line connecting them will be the line parallel to the force. So first off, can anybody tell me which direction F12 points? You've got some choices: right, left. Okay, you can include up or down, or up and to the right, or up and to the left, and all that stuff, but really it's going to be right or left because they're point particles and they're lying along the x-axis. Okay, let's start with an easier question.
Is it right?
Someone said right. Yes, right is correct, because they're unlike charges. That means they're attracted to each other, and we want to know the force on the left particle. Since it's attracted to the right particle, its force will point to the right. Okay, so we know the direction now. What's the magnitude? Well, excuse me. Well, F12 is equal to essentially, well, we'll just say 8.99 times 10 to the 9th newtons meters squared per coulomb squared times 0.333 times 10 to the negative 3 coulombs times 0.333. Notice I didn't use the sign. Times 10 to the negative 6 coulombs over 2.00 meters squared, which I think you can see 0.333 times 0.333 is 0.111111, which is really 1/9. And that's nicely cancels out with the 8.99, making 1. Similarly, 10 to the 9th times 10 to the -3 times 10 to the -6 gives me 10 to the 0, which means 1. So I ultimately get about, let's make it big so you can see it, 0.250 roughly newtons to the right. Okay, now I just chose quick numbers so I wouldn't have to even rely on you guys to do calculations or anything in that particular case. But does everybody understand how that worked? All right, I've actually run out of time. It's time for you guys to go. So we're finished here. I'll wait for the last person to leave in case anybody has any questions. But I'll tell you, go ahead and go to my YouTube channel. You'll see some calculations. They'll usually be in the month of January or in the month of August or maybe in the month of July. Okay. All those videos with those sort of dates and the PHY 242 will have calculations like this, but you can usually just tell by the title. So I'm going to do some more next time. In fact, we're going to have to use some calculus and all that good stuff. So you guys have a good one. Thank you for coming. And like I said, I'll wait for the last person to leave before I sign off.
Professor Younger,
Yes.
is the textbook for this class, is it the same one from last semester?
It is technically last semester. We were using the 5th edition. So if you were in my class last semester, you already have rights to go into the same physics course. You just have to go in, use your account, and they should let you. If you don't, you need to contact Pearson or My Lab and Mastering through their contact number.
Okay, got it.
Okay.
Thank you.
Oh, some people might have bought, like some people were buying like 120-day passes or something weird like that. If that's the case, you might actually have run out, but we were trying not to sell any of those. So hopefully you didn't get that, because sometimes you can literally buy one for just 1 semester, but if you have to take 2 semesters, it would bite you.
Yeah, so I took your physics 1 class in the summer, so I don't have the Pearson
Oh yeah, so
thing
you'll have to do it
anymore.
again. Yeah, we
Yeah.
couldn't use it anymore. I'm sorry.
That's okay. And
But you can
so,
still use the
but
old book, so just get an electronic access and you'll be good.
okay, so I have I think the 4th edition book. Is that still okay?
Yeah, like I said, they don't separate it from the online service. So when you buy the activation code to use My Lab and Mastering, you'll get the 5th edition for free as an ebook.
Oh, okay.
But you can still
Okay.
have your hard copy or whatever copy you have to read and to work with it. So you still have a nice physical textbook that you can hold too.
Okay, thank you.
You're welcome. See you, Maya. I think that was Maya. Anybody else?
Nope, thank you.
Thank you, John. John, sorry. Joseph, Ethan, you guys have any questions? All right. Well, it looks like everybody's.
Oh, actually, sorry, I'm sorry.
No problem.
I do have one more question.
Go for it.
So for the labs, I noticed Professor, is it Raskovich? Am I saying that right?
Yes, Raskovich.
Raskovich, okay.
Mhm.
So I noticed she had posted the first lab. The posts for the lab, is that something that's expected to be done before the lab, like a pre-lab, kind of like in chemistry, or is it something that we
She
do
probably
during?
has something like that going with her lab. I know she likes to do a lot of little things like that. So that's probably something she just wants you to read beforehand, or maybe even
Okay.
think about and do it. I don't know. On the first lab night, though, if you haven't met her yet, obviously, unless she sent you an email that specifically said for you to do it, I don't think she'd hold you to do it.
Okay, got it. And then another question is, so it's been about a year since I took the last physics class. Is there and and this is something I've noticed when I took the first one as well. But would you have any like recommended classes that you think is like something that I should have taken before I take this class in terms of like mathematics or like, electrical engineering classes,
Believe it or
things like
not, it's
that?
kind of a weird thing. Engineers, physicists, chemists, they are constantly learning, let's say, math from a non-math instructor.
Mhm.
And they're constantly learning, probability from a non-statistics teacher. And that's just the nature of it. So you're really technically only required to have finished Calculus 1, and I think this course might require Calc 2, just so
Okay.
you had a pretty good number of hours in doing integration. But from there on out, I'm teaching you everything. So we're literally learning sort of what a third semester calculus course covers. But to be honest with you, most of the the calculus courses I've taken are been related to at NC State or Chapel Hill or East Carolina. Their third semester course doesn't get into vector calculus. Usually they do some multivariable calculus and they do some analytic geometry type stuff, but they very rarely get to surface integrals and line integrals and curl and divergence. They maybe get to the generalized chain rule. So what I'll be teaching you is something that often would not come until at least a class after calculus, if not after differential equations. So yeah, there's nothing like that, but you are going to be learning some stuff from me that you might have felt more comfortable having a math teacher teach it to you. But I'll be honest with you, I taught myself differential geometry when I went through grad school for general relativity. And then I took a differential geometry course under a mathematician, and it made no sense. And in fact, by the end of the semester, we just started doing the very first thing we did the first day of physics. So it wasn't, wasn't that helpful.
Okay, sounds
Right.
good. Yeah, I was just just being cautious because I'm not like inclined in mathematics as I'd like to be, and it
Right.
takes me a little bit of time to catch on. And so when I noticed that in physics 1, so I didn't want to run into that same problem again.
Right.
So
There will be a little of it,
so
but my students do really well. So I mean, I'd say
okay,
it'll look scary, and you'll probably be scared every day, but somehow you'll pull
okay,
through it. Okay.
okay, I'll do
So
my
that's the
best. We'll
nature
see.
of it.
All
Yeah.
right,
It's
sounds
called
good.
vector calculus, though. So if you want to look it up and stuff like that, you can
Okay.
find a lot of cool things online that explain some of it to you. We
Mhm.
don't go as deep as you might think. I mentioned some things
Okay.
that are really deep, and I even show you a few things that are really deep. But what you have to do is really, really quite rudimentary, and I show you step by step how to do it. Okay.
Okay. Okay. Sounds good.
So
Thank you so
don't
much.
worry, man. You're probably make an A. No problem.
All right. Sounds good. Thank you so much. See
You're
you
welcome.
next time.
See you then.
Bye-bye.
Bye-bye.